Today, let's talk about a completely different approach to image editing compared to diffusion models. It is called the Visual Autoregressive Model, or AR model for short. The key question we will answer is, why can AR models achieve true training-free editing? First, we need to understand that the generation logic of AR models is neither diffusion nor reverse diffusion, but sequence modeling. It transforms an image into a sequence of discrete tokens, predicting them one by one in a certain order. This mechanism is very similar to language models, both predicting future tokens based on past context. What advantage does this bring? The generation structure becomes locally accumulative, cacheable, and editable. You can retain the previously generated tokens and only modify the subsequent generation path. In other words, as long as we know the token indices used to create the original image, we can precisely locate the regions that need editing, achieving minimal and targeted changes. This is the core idea behind our work, AREdit. The entire method can be divided into 3 steps. Step 1. Cache the token information of the original image. We feed the input image into a pre-trained AR model and record the token indices, probability distributions, and attention maps used at each generation step. This information acts like the fingerprint of the image generation process, forming what we call the randomness cache. It serves a similar role to structured noise in diffusion models, but with finer granularity and stronger controllability. Step 2. Recompute the probability distribution with a target prompt to create a fine-grained mask. We perform another inference with the new prompt, obtaining a new token probability distribution. Then we compare the changes between the original and new distributions at each position. If the original probability for a token drops significantly, we determine that it should be edited. This generates an adaptive mask that precisely marks the tokens needing modification. Unlike traditional spatial masks, this is a token-level probability mask, offering higher precision and less interference. Step 3. Reassemble the tokens to generate the final image. Using the previously generated mask, we decide at each position whether to keep the original token or sample a replacement token based on the new probability. This process is like puzzle piece replacement, achieving precise local edits while maintaining global consistency. Low-frequency structures are preserved, while high-frequency details are adaptively adjusted according to the new prompt, resulting in the final edited image. The entire process requires no noise inversion and no model fine-tuning, making it fully training-free. Another advantage of AREdit lies in its efficiency. Since caching is done only once, the editing stage requires almost no repeated computation, allowing us to complete one edit at 1K resolution in just 1.2 seconds on an A100 GPU. Compared to the tens of seconds needed by diffusion models, this brings nearly a 10-fold speed up. In summary, diffusion-based editing relies on reversing noise, which is unstable and difficult to control, whereas AREdit leverages the generative properties of AR models to perform direct token-level replacements. Caching, masking, and reassembly together form a complete training-free editing pipeline, preserving the structure of the original image while achieving precise local modifications. In the next episode, we will dive deeper into the fundamental differences between AR and diffusion models in editing tasks. See you next time.